Okay. Let's start out with going in order, I guess. So we can go with uh good luck, have fun. The group's all ready.
Sounds good.
All right.
You guys see the slide?
Yep. Looks good.
Cool. Kennedy, are you here?
Yeah. Sorry about my internet. 'Cause I think it's laggy.
No worries. You guys ready to start? Here.
Yep.
Kennedy, you're good to go?
Yep.
Cool. All right, Pierre.
All right. Hi, my name's Pierre Vargas, and our topic for this project was minimize remote devices in cloud computing. We wanted to look at what tech is out currently and how it shows that the direction of the industry is shifting from local systems to server-based ones. And we wanted to show how that shift could affect everyday devices like your personal computers, TVs, gaming, and other technology further in the future. For my portion, I'd like to talk more about what this can look like practically. If we look at the technology that we have now with things like smart televisions or smart TVs, we have already made some new ground with this idea. Our TVs are just monitors that connect to Wi-Fi and display whatever we ask it to. With the incredible advances that we've made while working in tandem with Moore's Law, as far as portability, those days are coming to an end unless we make some breakthroughs in like Ant-Man tech. We're pretty soon going to hit a wall when it comes to making things smaller. But focusing on the client's perspective, technology can continue to advance at a likable pace if we reallocate some hardware. Now, in our project proposal, I spoke about the possibility of one day taking a screen and controllers to the park and being to enjoy an online match with your favorite first-person shooter. This can seem far-fetched for a couple of reasons, but once upon a time, it was unheard of that we would have computers on us at all times, being able to stream movies and music from anywhere. Additionally, and I think I already mentioned this, the technology that makes this possible is already in use. For example, PlayStation already has implemented a mobile app called Remote Play. With this app on your mobile device, you can connect to your PlayStation from anywhere, as long as you have a reliable internet connection. What I want to emphasize is how this application utilizes your mobile device as a screen to stream the processing that the actual physical console in your home is doing. You, with your minimized hardware, are not generating the graphics, you're just streaming. And this is the kind of setup I mean in reference to like our personal computers and other devices. All they would need is that Wi-Fi connection and to interface with whatever hardware you're trying to use. Now, something to note on this remote play setup is the way input works. Currently, the mobile device functions as both input and display. This means that one device, the one we're trying to minimize, is supporting twice the traffic. This is like if we hooked up a console to a TV, but also hooked up a controller to the TV. Now, one connection is supporting twice the amount of traffic between the TV and the console, and the input data actually travels further, going from the controller to the TV to the console. The more efficient approach for this example is to connect the controller to the console, like what we do. So that's what we would like to see implemented in the cloud computing version. What that would require those controllers, and if you want to bring the rest of the picture, keyboards and mouses or mice, all with the Wi-Fi connectivity. Here's where we start to see another issue: internet traffic. With more devices connecting to the internet, we're going to need a way to sustain those connections. The only way feasibly to do that is to improve upon the infrastructure that provides our internet connectivity. Companies don't typically like to do that. They often opt to piggyback off of larger companies or build the bare minimum that they need for their service because infrastructure is expensive. But the infrastructure will be needed to implement our cloud-based idea. Currently, even with the technology that's already nearly accomplishing our goal with cloud gaming, there's a noticeable difference in the quality when it comes to like the display output. On the next slide, I've got 2 photos from a PS4 game. The image on the left was taken from the console, and the image on the right was a screenshot from the iPhone 10 that was running the Remote Play app. There's a noticeable difference in the quality of the display, as the one on the left shows 1080 resolution, while the one on the right shows about 720. We know that the issue is the connection speed because the iPhone 10 has the 1080 pixel resolution. We think then that the way forward is going to be improving on that infrastructure because the current infrastructure just isn't able to support the kinds of computation we're wanting to support. With that, I'm going to be handing it off to Mike so he can continue the presentation.
Thanks, Pierre. I'm going to continue this discussion of cloud computing with cloud gaming specifically. Gaming via cloud, as Pierre stated, is innovative and a very appealing idea. And when it's implemented properly, it's frictionless and allows for that minimized setup that he was explaining. So why are companies interested in cloud gaming? Well, money is a very large factor. As of 2021, the gaming market was worth roughly $200 billion. And the forecasted growth of this industry shows predictions to roughly 2 to 3 times that by 2030. The financial opportunity is tremendous, and large corporations, which we know of, have taken note. These corporations include Google, Microsoft, Amazon, and NVIDIA. They've introduced us to cloud gaming platforms such as Stadia, Xbox Cloud, Luna, and GeForce Now. And after trying a few services myself, I found that Stadia was the best overall experience when playing a game such as FIFA. It was a 1v1 online match. It allowed me to connect and play on my web browser without any trouble, and the video quality was definitely acceptable. I also didn't encounter too much of an issue with latency. I also found that I could download the Stadia app on my TV. And while I noticed the latency a bit more, it still wasn't a big deal, especially if I were to play a local match with a friend. My experience was not the same with the with Xbox Cloud when playing an online 4v4 match of Gears of War. The game was just unplayable, as I mentioned in my proposal. However, I did take into consideration that it was a much more demanding and latency-sensitive game. To achieve a pleasant experience with higher demanding and competitive games such as COD and Halo and Gears of War, the latency issue will need to be drastically improved. And I'm not discrediting cloud gaming in its current state. As I stated, FIFA was an enjoyable time, and all you need is a browser, a controller, and a reliable internet connection. As you can see, when I tried cloud gaming on Halo, I wasn't bearing any of the burden when running the game. The most frustrating problem with online gaming is lag. Everyone has experienced lag or latency. If it's significant enough, it becomes very hard to play the game, and it's just not a pleasant experience. So to realize cloud gaming to its fullest potential, latency must be addressed. 3 types of latency we have are client, server, and network. Client latency is the time it takes to register the user's input and the time it takes to output incoming information. Server latency is the processing time for the cloud provider's hardware to do any rendering calculations, such as graphics. Traditionally, a console or a PC would have taken on this task, but with cloud gaming, we're trying to eliminate that component entirely. Network latency is a sum of various different tasks. This will be the time it takes to access the ISP and the transmitting of data to multiple entities. Overall, for an enjoyable competitive online experience, the target latency is less than 80 milliseconds. Server latency is heavily dependent upon the hardware that the cloud service providers use. Currently, server and client latency amount to roughly 40 milliseconds. Client and server latency can definitely be improved upon, though, with better hardware. This would potentially improve the client and server latency by about 25%. But when you take that into consideration, that's only a 10 millisecond decrease. This means we're limiting the network latency to no more than 40 to 50 milliseconds for round trip time. Also, this round trip time must remain constant. Reducing network latency will be the #1 factor in optimizing cloud gaming, especially now that much more data will be sent over the network. This leads to new network congestion that must be overcome as well. However, improvements are being made in this field. Recently, 5G was introduced to improve mobile device speeds. Also, fiber optic cable is replacing old infrastructure and is more capable. Other innovations within the network are cloud providers are working with internet service providers to implement edge nodes. This reduces the travel distance of data and improves latency issues within the network. And some more ideas that have also been brought up are compression algorithms to help with the influx of data congestion as more data is currently being transmitted on the network with cloud gaming. Optimizing cloud gaming is plausible, and the companies leading the way do have the financial pool to do so. Cloud gaming is more than just a neat idea and a business plan. As we can see, we have models including social media, content streaming, storage, and applications within the cloud ecosystem already. So why is cloud gaming so important? Well, none of these other industries that were mentioned requires a high-speed, latency-sensitive transactions more than gaming. Ultimately, cloud gaming is the pinnacle. If and when it is conquered, all other cloud-based models will benefit. As the saying goes, a rising tide lifts all boats, and cloud gaming is that rising tide. Now to Kennedy to continue with this discussion. Thank you.
So for our final topic that we wanted to explore and look into was future applications on minimizing remote devices. So we took into an understanding that if technology trends furthered and into the pattern, then have other technology like advances, you could use the same idea of minimizing clutter with machines and transfer to the cloud computing. So there were two main points that I wanted to focus on, and through several articles that I found, those 2 main points that I found were interaction devices and using the same kind of system analysis. So for interaction devices, the first study that I found was into full body interactions, and they experimented with the possibility of human-centered computing. And so they would take a 3D aspect in games, but allow your full body motion to capture and place you into the character of the game and integrate with the type of platform. So for that specific research experiment, they had a helmet called a mocap, and it basically was created to allow servers to read the motor rehabilitation and process and correct errors in movement. It tracks movement of the user using technology, just like how movies and entertainment, how they have all the electronic stuff on them, and it basically transfers it into the computer, whatever happens on there. And so whatever motions are captured in real time, that's then displayed into the screen for active gaming. Another point was tactile sensations, and it's a reference to the study for remote tactile feedback called the Phantom Station. So that's a device attached along the forearm, and it senses stimulations and oscillations of the skin. So the purpose of that was to find an illusion of when 2 or more tactile stimuli are presented simultaneously to the skin, and they wanted to find cues in which touch interaction is able to use the findings to improve with virtual elements. So using slight movements of your hand could be transferred into a user's environment with technology. So with like future technology and human interactions with computers, like a slight movement of your finger could possibly move your mouse and zoom in on something or click something. You don't actually have to physically touch it. So these connections with our brain will allow us to do this at some point in the future if they figure it out. Then with using the same system analysis, a study into water systems planning and management used the idea of gaming maps and spawn points to use as tools for economic issues related to water management systems. So the computer modeling took stakeholders like conflicts and they were trying to resolve it through a gaming platform. And they wanted to build the idea of using simulations and collaborative models with new policies and being able to monitor and analyze like pressure changes and stuff, how it would actually be in like the real world, but doing all that through a gaming system. And you can kind of change it, make your own trends and see like what would actually happen. And so the specific goal for that analysis was just finding a solution that minimizes the costs, and duplicated pipes is what they used in that experiment. And then also for virtual mailing system, that was just like another big point that was pointed out that could happen in future applications, which instead of going to actual malls and stores and stuff, they pretty much want to eliminate as a whole, which that would be your console and devices. So then everything would become virtual. So then the next thing was just pretty much, I had some images of what each of the studies showed. So the one on the right was the interface to show the games, how like the players could control pressure and where they wanted to have everything for water systems. And pretty much they would create the game on their own. And then the tactile feedback is where the hand is, and it kind of shows where the pressure points are and how that could convert to where it goes into technology. And then the mocap is kind of showing a representation of them wearing the cap, and it puts their body into an actual game system. And then we have our responsibilities. So we kind of just split up within our topics of the minimize hardware, latency, and then feature applications. And then, so for the conclusion, we were able to review the idea of minimization of devices and the effect that latency would have on it. We were able to discuss the user friendliness of it and how the quality is affected in the cloud state, how Michael and Pierre showed. And then future applications in this state can also take technology to a much bigger place in the future. And then we have our references. And then if there's any questions.
Yeah, I got a question. What do you think, because I think Nelson asked, like mentioned it before, what do you think is like the most challenging thing to change in the infrastructure?
Yeah, so I mean, just with like traffic, we kind of need like better coverage, better internet coverage, better, whether that's like through like you can go places with your phone, right, where you drop service and oh man, shoot, I can't drop, or I can't download this video or whatever. So I mean, if we want to implement, you know, that kind of cloud gaming to where like you can, your device, your display can just kind of pick up your signal or connect to your computer from anywhere. You need that because, you know, now you're needing a Wi-Fi connection to do things that you didn't need Wi-Fi for before. So it's like if I'm, yeah, I don't know, like for example, the game I was playing that I showed with the 2 images in quality, that's like, that wasn't an online game, but I needed Wi-Fi to play that remotely. So like I can play that anywhere I have Wi-Fi. And that's how it's like more mobile. But like if I want to, yeah, go down to the park and play that game, I could, but I need Wi-Fi connection. It's like that's not somewhere you typically have Wi-Fi connection, or like data connection even with your phone. It'll be a lot harder to play that game. So that's kind of what we mean with the infrastructure. It's like that support for Wi-Fi in like, yeah, like just widespread. Yeah, you need better signal, you need like signal towers, you need, yeah, better connectivity in that sense. And like that's not going to come by upgrading my phone. It's not an issue with my phone. It's the infrastructure of the coverage.
I gotcha. Thank you.
I've got a question for Michael.
Yeah, go ahead.
You said you tested Stadia with FIFA. Do you know what your connection speed was?
I couldn't tell you that. I didn't actually look at the exact connection speed. What I noticed with it though is, I mean, I can tell you what I know Spectrum, I get, I think about 220 megabits per second download. But what I did notice with it though was while there was just like it's a slight delay in my movements, it definitely was like still playable. Especially with especially when I went into an online game, I didn't really expect to have that control going into an online game, because the first time I tried cloud gaming was with Gears, and it was just, I mean, even the single player Gears was just not playable. So I was very impressed with Stadia.
You said you tried Gears, but what did you try that on?
I tried both of them on my, they were both on my computer, but via a web browser.
On Stadia?
Yeah, I use my web browser for Stadia as well. I tried Gears on, I'm sorry, I tried Gears on Xbox Cloud, and then I
Okay.
tried FIFA on Stadia. So I was more impressed with Stadia. So I know it's not like a one-to-one comparison. But again, I just didn't expect to get that that quality of gameplay with cloud, and I was pretty impressed with it.
Yeah.
Is there any other questions?
All right, doesn't seem like it. So let's see.
Okay.
All right, thank you very much.
Thanks,
Yeah,
guys.
thank you.
Thank you. So we can move on to our next presentation with Latency Boys.
Can you guys see the slides?
Yeah.
Yeah.
So hello everyone, my name is Al-Mu'tasim. Today me and my group members Anthony and Ivan are going to present about cloud gaming. We're going to focus more about an issue that cloud gaming has, which is latency. So let's first define the cloud gaming. As we stated before, the cloud gaming is playing video games in a remote server without needing to use a computer with high features and high storage. So the user does not need to spend a lot of money on buying that computer. But cloud gaming has so many issues that can distract the player while playing, such as high internet speed availability, video compression, and latency. We'll be focusing more on latency, and we'll be providing solution for these problems. So latency means a delay. This delay can be easily noticed while the player is playing video games and trying to send commands and action and waits for the reactions to happen. And this short period of time when the reactions come in called the latency. So how does the latency happen? The latency happen because of many different things. First, it can happen because of the devices that the user is using, such as the monitor or the controller that the user is using for playing video games. And this problem can be solved by replacing these devices with more developed devices. But the second problem, which has the highest effect on latency, is networks. So networks can change the latency for many reasons. First, if the connecting data center is far away from the user, the latency will be high because the data will be need to send from router to another until it receives by the user. So this causes latency, and the longest the data takes to arrive to the user, the highest latency will be. And this problem can be solved by connecting to a close connecting data. And the second problem happens when the user uses a satellite for connection. So satellites work on sending wireless signals, and these signals work on transferring data. And these signals can be easily damaged or affected by the nature and object around the user, which causes latency. And this problem can be solved by using Ethernet cable, which is a better solution for the for gamers. This problem should be solved by the companies that runs cloud gaming, so they can attract the gamers and give them the best cloud gaming experience. In order to solve this problem, we have done some researches and we found some solutions and technologies that can solve this problem. I'll let my friends to explain more about these technologies and solutions.
I'm Ivan, and I'd like to start with saying dynamic gameplay. Dynamic gameplay is the process of changing some aspects of a game in order for it to be more enjoyable. Some examples of this are changing difficulty and changing image quality. For changing game difficulty, one such method is to determine the bitrate of the connection first, then to use that to dynamically adjust areas of hitboxes. This is important because in a frame rate dependent game, such as a first-person shooter, the objective is to shoot the target and move on. When bitrate is low and frame rate is low, accordingly, the user will be frustrated due to missing shots from latency. So a compromise to keep the user happy on lower bit rates, which is connection speed, would be to make the game easier. As you can see on the screen, the image shows us on the right a standard set of hitboxes on a person. We see that the red area will do the most damage and that the green will do the least. On the left side, we see a singular, much larger hitbox surrounding the person. This larger hitbox will be easier to hit, and therefore the player will still get some satisfaction. Games like Fortnite do not need to worry about this because they compute hits on the most recent frame the shooter sees. This means that any game that, although gameplay might still have latency, this is less important since players can compute locally. This is precisely the issue with cloud computing. The server computes the hits based on the action the user made on a previous frame. Can you go to the next slide, please? Compression. Some compression I would like to talk about is VP9 and H.264. As you know, compression can change aspects such as size and image fidelity of an image, meaning sharpness of the image, or the resolution, as well as the color of the image. All these changes will make a compressed image less appealing. As you know, Google Stadia is a large cloud gaming provider, and the image on top shows us a comparison between their graphics and the graphics of the Xbox One X. Agreeably, one of these images is more visually appealing. The one from Google Stadia misses some definition on the player, which makes you question if the player is important. H.264 is a well-known and much-used compression format for video compression. This compression is mainly for HD videos. H.264 is a block-oriented compression which samples an image and matches corresponding samples together and basically sends the client those samples as well as all the locations that match on the image. That is, if I had a dark image, all the dark or black parts of the image will be sent to me as the sample. This loses some image depth as well as sometimes making the output look blocky, which is what we saw in compressed videos on YouTube a few years back. We would see the blockiness. VP9, however, uses a super block approach. This takes a 64 by 64 block of an image and compresses smaller blocks ranging from 32 to 4 by 4. This is important because it lowers the chance of the final image appearing blocky. Along with fixing the blocky images, VP9 also supports higher resolutions and a 720p video that can run on the same bandwidth that a previously 480p video could handle. In Google Stadia, though, the main compression format used is still H.264. This is because VP9 is reserved for 4K resolutions, since it works more efficiently on higher resolutions. One problem that may arise from VP9 compression is support for it. Maybe our streaming devices may not be able to handle it, but this is not the case. VP9 has been running on YouTube since 2013 and has Android support since 2013 as well, meaning today's devices are more than capable of handling the compression. I also want to talk about the activity importance model. Oh, can we go to the next slide, please? Oh, actually, never mind. The activity importance model discussed in another paper, the image on the bottom demonstrates activity importance, which is a definition of what an image is important. We know that the people and faces are important as well as text. In a video game, this is true as well. What is less important are things like background and scenery, except we do not want these gone entirely, as the context of the image is still important. From the paper we found, it is seen that the activity importance model on compression improved people's perception of the image. 71% of people said that with manual attention modeling, the image looked better as compared to the direct downsampling, which is just standard compression. And I will hand it off to Anthony.
What's up, everybody? My name's Tony. So I'm here to talk about service mesh technology first. This is a technology that's fairly new and becoming more and more popular. A service mesh interface is basically dedicated to service-to-service communication amongst a cloud-based network. It will sort of handle, micromanage incoming service requests and kind of allocate them to the most appropriate server. This can improve communication amongst the servers and within the network, also improve reliability. You know, a typical application will have hundreds of services within you know, a given network or its network. So it can be sort of difficult to kind of monitor all of these services and make sure they are, you know, readily accessible for the user, and sort of there's no delay in, you know, a service request or inquiry. This technology also helps to define like a set of standards or regulations that'll kind of help you know, measure traffic control and traffic metrics. This will help with like splitting traffic and allow for you know, the application or the networks to kind of relieve servers that are that are being overwhelmed with services or that are overcrowded at that time, and kind of pick one that can handle, you know, a given request. A recent application of this in the market actually is Xbox managed to secure 22,000 pods of servers, which is just like clusters of servers that, you know, kind of either are in the same vicinity or work together. This was done using a service mesh technology known as Linkerd, which kind of does exactly that, sort of help monitor these servers within these clusters on like the software side of things, if you will. You can go to the next slide, Alma. So I actually think this technology was mentioned in the previous presentation. Edge technology involves using edge nodes, as you can see, to sort of ping servers that are, you know, closer to the closest to the user to minimize the pathway of a streaming video game. This will the required bandwidth for any video game streaming, I think, heavily depends on the bandwidth required for the pathway from the user to the cloud data center. So obviously the shorter that is, the more optimal the bandwidth usage. So that will obviously benefit cloud gaming in that, you know, cloud gaming is a highly user intensive, experience that requires, quick responses to the user input and, you know, yeah, and so that'll definitely reduce the latency and sort of reduce the network delay, which kind of go hand in hand. The Edge game framework is another specific application where this was experimented with. They used what is called the NAGS algorithm, which is the Neural Adaptive Game Streaming algorithm, which will adjust the bit rate accordingly as the bandwidth changes. Because as I say, if a mobile gamer decides to walk, to another room or decides to go to another place, or, the distance between these servers and the user will change. Therefore, the bandwidth will kind of fluctuate, and this algorithm will kind of, negotiate that, and that it'll change the bitrate accordingly to kind of give the best experience for the user and smooth out the gaming sequence. The Edge game framework that was recently experimented with, I think like a few months ago, was able to achieve a network delay of right around like 16.2 milliseconds, which I think this was mentioned before as well. Like the typical cloud gaming network delay now is right around like 50 milliseconds. So this definitely can be successful, and it's definitely an intriguing option to reduce latency for sure. You can go to the next slide, Almo. So in conclusion, in general, it seems like video games have become increasingly more and more popular, especially with our generation. And with that trend, of course, cloud gaming is going to become more popular. With technologies that we've mentioned, it has extreme potential, convenience, and sort of makes video games more accessible than really they ever have been before, which is definitely cool. And as you can see, this is the projected market cap of cloud gaming in 2024. I don't know why they put it in thousand millions. I think that is 6.5 billion, if I am correct. So definitely profitable and marketable. And I think that's it. These are our references, and if anybody has any questions, feel free.
I wanted to ask a quick question about an earlier topic they had about compression, and it just the diagram that you showed leads me to believe that that form of compression would favor some games more than others, because in say a fighting game, the elements in the top corners all the corners are just parts of the UI, and you don't need to see them accurately too much. But in something more like what you said, like Fortnite or Valorant, those are games that if there's a small change there, you need to be able to see what exactly it is and react off of that. So do you feel like the compression is kind of a momentary solution, or do you think that's basically what improvements do you think need to be made there, or do you think it's fine to go as is?
Elmo, can you go back a couple slides? That one. All right. You're talking about this picture, right? The one on the bottom?
Yes.
And the image on the right, B, that is the weights of the image. It says that the middle is more attractive to the user, which is somewhat true. In like games like Fortnite, the activity importance would be like the users on screen, like the opponents on screen would be important to see, so they would compress them less.
And so therefore they wouldn't just blur into the background. You would be able to see them, and you would still have a much smaller file if you have just a little bit uncompressed, as opposed to everything compressed equally and just a worse image.
Yeah.
Any other questions?
All right, doesn't seem like it. So we can move on to our next presentation.
Thank you, everybody.
Got mobile monkeys.
All right, I'll share my screen. Okay, you guys ready?
Yep.
Yeah.
All right, so this is our project. This is going to be the impact of mobile cloud computing in relations to social media specifically. And next page. So what exactly is cloud computing? Well, cloud computing, I'm sure everybody in this, breakout room should know it. Essentially just using somebody else's like systems resources, using like their, either storage or like computing power. And this is especially like important when it comes to talking about mobile cloud computing. And mobile cloud computing essentially is just normal cloud computing, but for mobile devices. And this doesn't exactly mean the device has to be mobile itself. It can be stationary like a tablet or a laptop, but it can just be on the move as well. And the problem with mobile cloud computing or like mobile devices in general is that they don't have the same computing power as a like full-on computer would. So that's where mobile cloud computing comes in to help step up that computing power, help save that storage. And this is closely related to social media because social media platforms, they have large amounts of foot traffic, large amounts of like data constantly going through at a certain time. And so this would mean like these large amounts of data would need to be computed, and it would definitely not be ideal to be computing all of that on your mobile device. That would just cause it to overheat, probably die out early. And so this is why mobile cloud computing is important in relation to social media.
All right, here we have some of the impactful problems we have found that pertain to social media as a result of mobile cloud computing. There's the quality of communication, and Nick will go more in depth with that shortly. Lack of storage transparency that Thomas will lay out, and insecure data transmission that Onsai will talk more about later on. On our right is an image showing the statistics of unique mobile phone users, internet users, and active social media users in relation to the total population of people on Earth as of April 2022, just to give you an idea of how widespread they have become today.
Right. So to start off with quality of communications, there are just two factors that I want to focus on for this presentation that are the general things that every single mobile user will experience that they will say determines what is the average quality of their experience, and that is how stable is their connection to the mobile cloud computing network, and how bad is the latency. Okay. Next slide, please. All right. First, for stability. Stability was a hard thing to just research because a lot of the things I was researching was how to like large changes to improve stability or small things to generally optimize it. But this is one of the best ones I found that went into detail about what the current state is. In short, because mobile cloud computing is reliant on first the cell phone infrastructure, which has been under development for the last few decades, into our server farms that will actually do the computations. Our mobile devices are actually very good at connecting to that network to begin with very consistently, because it has been a very big issue for decades, again, that our phones need signals. While we might not always have Wi-Fi, we will always be able to use some amount of data until you are completely out of range of those cell phone towers. So for stability, the biggest change would be in the physical layer of the processes, but basically the majority of the issue is just the bottleneck of how many users are using the servers at any given time, which is something that we can deal with by more server farms, efficiency like that. That's a whole thing that's worth another entire PowerPoint. For now, I just want to focus on one article that I read that was good, that talked about a possible change of the core infrastructure using cloud radio access networks instead of the current infrastructure, which they now believe that has been developed to the point where it is consistently able to make an improvement on the stability and the latency. As you these two graphs here show that there is a improvement, although small. So this shows that there is still room to be improved. Oh, and there's still room to be improved on both the sides of stability and latency, but it requires a large change to the infrastructure. And for the record, these graphs are just simulations of what this new physical layer in an altered link layer would be, because the purposes of this, those would be the only two layers that have any changes. The other three layers would be able to remain the same. There's no issue. All right. Next slide, please. Now for latency, as all of you are informed, there's a lot of things that contribute to latency. This is a very big problem. I'm just going to focus on two individual layers so that way I can just go through this a bit faster. There is still optimizations to be made to our current set just for latency, small things. I'm going to be focusing on the physical and the application layer for this. The graph on the top right is what's referred to as a call graph, which is a visual representation of how the computers are computing in the application layer. Each T there is known as a task node, which will receive and give information until the task is done. Each V node is representing a CPU cycle, or the amount of CPU cycles to complete the task. And this is just a good way to just visualize it. Oh, and the very top of it is known as the determining variable, which is how, and unlike a lot of computers where it is going to the cloud computing network to do a certain thing, mobile devices are very pick and choose. Like a computer can do a game, but it can't do one of the best games right now. A mobile device could be able to run a game, but at the moment how they are running is, if it is in a category, it is always doing it on the device. And if it is not in that category, it's always in the mobile cloud computing network. So for example, your phone is great at handling pictures and doing anything like that. An app can give you additional filters to add into that, but that's all on your device. Uploading that picture would require use of the mobile cloud computing network. So it is always going to be either, even if it's small, it's always going to be on the cloud network if it needs to. If it's a really heavy issue that even if it would be faster on the cloud computing network, your phone's going to do it, because it's just, it works out to, that is the best way to do things. On the bottom right is now the basic formula for calculating latency of just the physical layer alone. It's a little tricky to maneuver around, and it's not always the best way to determine things, because that n variable stands for noise spectral density, which is not really something that you can control or even regulate. But it is a good general thing to just test different solutions, see if there is an optimization to be made. The B variable is also bandwidth. Y is referred to as channel gain, and P is just general power. But in quick summary, that is just about what I've learned trying to look into the quality of communications for mobile cloud computing. And now we can continue on with, I believe it's Thomas next on the next slide.
So here we're focusing on the issue of lack of storage transparency and specifically breaking up into 3 different parts, starting off with issues due with data loss. And specifically what I researched was data loss for legacy data. And legacy data is just a term that means like information that was stored in like an older format and like obsolete format. And or like a different computer system. It just makes it like a more difficult to access with like modern file formats and such. And like these sorts of data generally come from the older generation who still has these types of data like accessible in their like old computers or something. And like this becomes a bigger issue when it comes to the big platforms that would be handling this old data. Because if they mismanage this file format, it's a format they're not used to because they're handling more of the modern file formats. And so a possible solution to this would be to create some sort of dedicated cloud server that handles the majority of the older file formats. So it'd be easier to observe and, you know, be more secure and be more noticeable when like these files could go away. But that brings up another issue such as like server space. You know, having just one single cloud would cause an overflow in server space pretty quickly. And so one of the research papers I've read discussed about a geo-distributed cloud. So this would be very helpful, especially in terms of including social media and well. Because instead of having just one single cloud that handles everything, we can have multiple distributed clouds, and this can be, you know, built based on popularity and like a number of users in this area. This way the users can have a faster way to access the cloud without being stalled. So for example, if we had one cloud in America and then we had a user in Europe trying to access that cloud, that's going to take significantly longer if there was just a cloud over in the European area. So this would, you know, help with foot traffic going on with social media, and, you know, having multiple clouds would also eliminate the single point of failure in case a single cloud goes down. We wouldn't have that issue of the cloud just shutting off and then everything going away. And then the last important factor to discuss would be data caching. And data caching is essentially, you know, where the data is coming in and it's processing multiple copies of the data or files in a temporary location. So we'd apply this by using data cache in the cloud. Cloud would be applying data cache. So and then a research paper I looked at created a prediction model to see when to use data caching. The model would essentially look at what the user is looking at, and then it would determine the popularity of the data that they're observing or accessing at the time. And then it would apply it to other users as well that would be near that user. So if a user was accessing video, and then the cloud would receive this and then be like, okay, this video is kind of popular, let's store that in the cache. And then potentially the user near this user would access it as well. And if they do, the cache is there and it accessed quickly. And this would just make things much faster. And the researchers used a CNN model to develop their deep neural network like model to simulate everything. And essentially they got a bunch of good results from it, and they understood how prediction model like worked effectively.
All right. So since mobile cloud computing makes use of the internet, it provides data transmission through an insecure channel, and thus a new set of problems occur. Users worry about the security of such a model and how they are impacted. So the development of some social media platforms as mobile cloud applications can be unnerving, with potential security threats such as man-in-the-middle attacks. Man-in-the-middle attacks are largely with intent to steal people's personal information. This happens by placing themselves in between the user and whatever application they use, which in this case would be different social media platforms. There are different methods like interception and decryption, but ultimately they breach and exploit any vulnerabilities in the network, web or browser. Sensitive information can sometimes be stolen, like usernames and passwords, which leads to impersonation and masquerading. Much in the way that man-in-the-middle attacks were to obtain personal information, impersonation and masquerading are aimed at the same. It is essentially when an attacker pretends to be someone else or takes on the identity of a legitimate person to gain access to unauthorized information they otherwise would not be able to. In this case, usernames and passwords obtained from the cloud through the man-in-the-middle attacks would also allow attackers to easily impersonate whatever user's information they stole. This can lead to problems of identity theft, sometimes involving like stolen social security numbers and bank account information. And everyone has heard of malware, but some don't know that it can also be injected into the cloud, referred to as cloud malware. They will inject a malicious service or like a VM virtual machine that are either related to one of the cloud computing models, so like software as a service, platform as a service, or infrastructure as a service. There are a few different types of cloud malware attacks, like DDoS attacks or exploiting live migration. Cloud-based social media platforms can be slowed and altered if left unchecked, and users can suffer from this vulnerability. The figure on the top right shows the different cloud security risks that could arise from this or from its implementation. The bottom right figure is a simple, like bare bones showcase of just how man-in-the-middle attacks go about. There is possible implementation of what's called a mutual entity authentication protocol for mobile cloud computing to combat this insecure data transmission. This protocol involves using like an OTP, which is just a one-time password for user authentication. The one-time password is basically created through like the concatenation of like your username, your password, and this value called like the IMEI number. This is from like your mobile phone or like your cell phone. After that, it is encrypted through a method called triple data encryption standard algorithm, or short is 3DES, which involves randomly generating a key to help with this encryption. There's also a key randomly generated from just DES. So based on some testing, this protocol has been through. I think they use like Java EE, which is like Java Enterprise Edition. It appears that it delivered better overall security for users in both authentication and data transmission.
So for significance, I just want to reiterate that there are several billion mobile devices currently in use, meaning there's a few billion users. Each user has the chance to use it every single day. And with the current rise in popularity of social media platforms, every single user has a reasonable demand to make use of the mobile cloud computing network. And because of that, any issue that is present, whether it's a small amount of latency, a security issue, or packet losses, have the potential to affect several million people easily, because at the end of the day, if it's an issue that only affects 1% of people, it is affecting a very large population with this platform because of the high population. So we just wanted to bring attention to some of the issues and just update you that people are still making improvements for the thing that we might even consider to be sufficient at the moment. Next slide.
Okay, so ultimately, this research was to grasp the relationship between mobile cloud computing and social media, following the different impacts it can potentially have. We wanted to better inform ourselves about how mobile devices utilize cloud computing and inform users of any potential concerns that may arise. Thank you, and we're open for any questions now. Oh, there's also references.
Can you go back a couple slides? I think it was yours, Thomas.
Sure. What's up?
Go back another. Oh no, sorry, 2 forward. I think. I know I'll see it once I. No, that's not it.
Earlier, stability.
CRAN. Oh, my bad. What is CRAN?
Oh, so it's okay. It's one of those things that, like, I read the entire research article for it, so it's hard to describe in like a short amount of time. But it is at the for the relevance of this assignment, it is just an alternative way to access for a mobile device would be able to access the nearest telephone node to then be able to go into the mobile cloud computing network. It is just a proposed change to the physical layer for our purposes.
So when it says radio, it actually means radio.
Yes, it would be a change to a radio signal that,
Okay, that was my question.
would be commonly used. Yeah.
Thank you.
All right, any other questions? All right, if not, we can move on to our last presentation. At Surf Team USA.
Surf Team UCF, yeah.
All right, oops.
No, it's all good. I'm just playing with you. All right, let me see. Let's share. It's making me authenticate. Hold on. It's saying that I got to quit out and join back in. Corey, could you share the slides by chance? New computer, so running into some issues. Sorry.
All good.
Or Chris. Yeah.
Can you see mine?
It says that you're sharing, but I'm not.
I can't see it.
Yeah, I can't see it either.
All right, let me see if I can share real quick.
It's honestly kind of impressive it took us to the last presentation to have an issue like this.
Yeah, right. It's got to happen eventually.
Yeah. So thank you all for taking the bullets.
My computer is not letting me either.
Cool.
I
might have to quit out and come back in now.
Okay.
I'll try it one more time.
Oh.
There we go.
See the screen.
You're back.
Can you see me?
Yeah.
Yeah.
Cool. All right.
Yeah,
That
looks
being
good.
said, Get rid of that. All right. Well, here we are. Hello, everyone. This is our final presentation, and it is on cloud computing and how it could change the gaming experience. I am Jonathan, and my two group members are Corey and Chris. So, what is cloud computing? We need a basic introduction before we start. So first things first, cloud computing at a high level is simply just the capability to use your typical computer hardware and peripherals like GPUs and CPUs without physically having that particular system that you're using, like physically. This being said, cloud gaming is just using these cloud computing services in the gaming industry. And why might we want to do that? Well, cloud computing and gaming allows the end user, or us, the user, to have a more economically efficient and hardware experience on our end. So we can kind of run less capable hardware with very high quality games, and they would still run, in theory, perfectly fine, and not, which would otherwise fail to run if you tried to run them on your hardware specifically. So we'll dive into some other benefits of cloud computing in the following slides. So this is a big one, replacing the need for personal gaming hardware. Might sound a little ridiculous when first said, but so was the idea of smartphones 10 years ago, you know? So here we are. With the proper infrastructure of cloud servers on the client side, the end user would not be as pressed to upgrade their hardware as often. So with the improvements in gaming, it's almost, you feel forced to upgrade to a new GPU every other year because you just want that newest, best experience. In theory, with cloud computing and gaming, you can kind of take a step back and pay a term fee to get the same benefits that you would be buying a real expensive GPU with. So that's kind of due to the fact that all the most pressing game tasks are handled by the cloud servers in the data centers from that particular provider, instead of from, as this flowchart shows, the thin client, which is the end user or us. So hence, this kind of allows the user to have less capable hardware at the end of the day, but could still enjoy very high quality taxing games. This flow chart right down here on your bottom right kind of depicts this process of how cloud computing works. And you can tell that it goes, that the end user, the thin client, doesn't have as much going on, but it is very key to have a good network connection to get the proper stream back. So globalizing cloud gaming. We can basically take these video games and spread the reach to them to many different people that wouldn't typically be able to use these games. And this can be limited, or not limited to, underspec PCs, tablets, Mac users, and phones, just to name a few. But not everything is a perfect world here. If you have to run other taxing applications on your computer, like Lightroom or heavy coding applications, then this kind of prohibits you from reducing your hardware, because you still need these on computer services, which require a lot of processing. That being said, as cloud-based services become more popular, it is likely to see many of these applications also turn to more cloud-based services. So this gap could likely diminish. And if you wanted to, you could pay a set of what I would guess would be subscription-based fees instead of the perpetual fees that you pay for a GPU and a nice CPU. There's also a handful of environmental benefits to replacing and minimizing your computer hardware for cloud gaming. The first of which is a study from The Guardian that we looked at showed that there was over 372 million units of e-waste last year in the US alone. Of this metric, basically 90% of it was computers and cell phones. So if you think about it, if you're going to take cloud gaming and spread it out to a whole handful of new users, this would press them to not have that always pressing need to upgrade their hardware, which in sense would drive down that metric of 372 million units, which would bring down the e-waste. And that is obviously better for the environment. The second thing is power consumption. All the heavy processing power that typically be used in your personal hardware is going to be minimized because now you're running it at a much lower level just from the thin client side. All this other heavy processing power is going to be to the GPU and CPU and all the other processing units of the data centers, which are typically highly optimized to save power. Because that's, at the end of the day, if they save power, they make more profit. So they're obviously going to be highly optimized. With all this being said, I'm going to hand it off to Chris now to explain some of the possible network improvement options that would make cloud gaming much more tangible in the future.
All right. Hey guys, how's it going? So you can go to the next slide.
Oh, that's not what we want. Sorry.
No, you're good. Okay, so in a couple of previous presentations, they talked about edge nodes, which is essentially what the idea of one of the research papers that we read, except they called it cloud fog. So essentially what these guys did is they took, they basically looked for corporations and organizations and gave them incentives to say, hey, whatever unused equipment you have, we're going to use as a supernode. Okay. And essentially the supernodes are going to allow for the clients to be, and the users to have a faster bit rate and also to have better bandwidth. Part of the presentation got a little clip there. Anyways, it says there's a receiver-driven encoding rate adaptation. This is one of the ways that they were able to incorporate this idea of the fog. Essentially, it's just so that if there's too much traffic, they would lower or increase the bit rate in order for the gaming experience for the user to be better. And that's the whole idea. When you're doing cloud gaming, you want to have the best quality of experience. But that also can come at a cost, right? A lot of organizations just say, all right, we're going to put more data centers, but this idea essentially lowers the cost of building the data centers. Anyway, there's also this deadline-driven sender buffer scheduling, which that idea essentially that idea essentially encodes the game video, right? And it puts the segments into the buffer to send to the normal nodes. But each supernode will send out video segments. And it basically, the segments have different packet loss tolerance and delay tolerance. And the whole point of it is essentially to improve the overall quality of experience for gamers. And through their research, they were able to get some pretty interesting results based upon these supernodes. So if you want to go to the next slide, that would be cool. As you can see on, let's see, they did a simulation essentially where they had two different kinds of algorithms using the clouds, well, three different, and essentially they compared them and saw which one used the least amount of bandwidth consumption based upon the number of players. Another thing that they looked at was response latency, which is pretty huge in cloud gaming. If you want the best experience when you're playing, you don't want to get lag, you know. Along with that, that's playback continuity. So making sure that you have continuous play, you're not crashing out of the game. And then also we wanted to look at how satisfied players were, you know, and based upon the super nodes, it seems like they were pretty satisfied up to a certain point, and then it starts dropping off based upon how many players there are. Another idea is also looking at quality of experience and lowering the cost. We're also looking at better overall performance, as we have discussed previously. This idea essentially is using virtual machines, and they looked at the idea of provider-centric versus gamer-centric problems, they called. And essentially the provider-centric issue was that oh my gosh, my brain just turned off for a second. I'm sorry. The provider-centric issue is that they would have these servers and the providers had to take care of them. But they wanted to take the virtual machines and which would allow them to not have to worry about so much of the rendering and all that kind of stuff. Well, essentially, they also looked at how the virtual machines would be able to process different games and different genres of games. And they also were interested in looking at reusing equipment that we already have, which is the idea of cloud gaming. You can move on to the next one. The results are here. They had two different algorithms, and then they also had a base algorithm. The LBP is the base algorithm, and then the LDH is one of the algorithms for provider-centric, and the, not LDH, QDH, I'm sorry. QDH apostrophe is the gamer-centric. And you can see that their algorithms outperformed the base algorithm in their simulations, and essentially allowed for the clients and users to have better gameplay. And also, they ran a simulation for World of Warcraft, and they were able to show basically how the price based upon the number of days still allowed for the quality of experience to be at what they called the minimum level, and players were still happy. So I'll move on to Corey.
Yep. Hey guys, I'm Corey. I'm going to be talking about some of the security aspects for cloud gaming. So just like any other cloud-based platform, security is a major concern. Obviously with your data just floating around, it's kind of always makes you a little nervous for sure. On the good side though, like most large cloud-based technologies, you have this top of the line security that they'll have for their servers, so your data isn't extremely vulnerable. However, there is always the incentive for that attack to happen because it's a mass congregation of a bunch of data. So that is always a concern. But on the other hand, you have it keeps the games themselves relatively secure compared to when people actually have the games themselves downloaded. Can go to the next slide. So the advantages of security. So as you can see with this little diagram I have over here, when you're using a cloud-based platform, you have this super thin client, and all you're doing is getting the video stream from the server and you're sending it the inputs. So as a result, any kind of like cheating where you have to modify the game operations, you can't really do, because you don't have any access. All the operations are being performed on the server. So that is a big plus. Obviously there's still some concern with like scripting, that kind of stuff. You could still have that. But the game executable file itself, you wouldn't have access to. So that would remove the problem of piracy. Yeah. Then some of the drawbacks. So you tend to have better security overall, but there's still some concerns. The game itself is running on the cloud servers. So if the servers were to go offline from an attack, or just because of too many users trying to access it at once, or if you were to lose connection to the internet for one reason or another, you also lose access to your games, which is no good, obviously. Also, all your user data is stored in the cloud. And like I said, that leaves it vulnerable to an attack, which is a concern with all cloud-based platforms. Yeah. Just to conclude, bring everything together. So in our research, we found that the inevitable improvements to network technologies will allow cloud gaming to completely overhaul the gaming landscape. This results in a more secure gaming platform, while at the same time eliminating the need for personal hardware. And we just have our division of responsibilities, as you saw throughout the presentation. And our references.
Any questions?
Yeah, I had one for Christopher. He mentioned super nodes, and then you were talking about the satisfaction based on how many players there are. Could you elaborate on that a little bit?
Yeah, so basically, like I was saying, the super nodes are what we talked about in previous presentations, like edge nodes. And basically, they would ask corporations or organizations to use their idle equipment, and that equipment will essentially serve as a connection closer to the player, right? So if they were looking at if they increase the number of nodes, right, based upon the number of players, how the response would look for latency, how the server bandwidth would look, and how satisfied the players were based upon their connection, essentially.
Gotcha. Thank you.
Yep.
Anybody else?
All right. Well, thank you guys for your time.
Thank you very much.
Thank you.
Should wrap up everything. We're done with all the presentations, so I think we can head back to the main room, see what Professor says.
Sure.